So some of the tricks we play to get this linear complexity, because it just, honestly, this algorithm is simple ideas and then just lots and lots of tricks to get it linear time. One of them is we never form eigenvector matrices explicitly. I said we have this hierarchy. So so when we do that, because at every level you have to multiply by the previous level. So instead of if you're at level 6, instead of forming the 5th intermediate eigenvector matrix, you just multiply them all online, one after the other, because this goes from quadratic to linear time operation for this. So that's an important trick we play. We do a lot of matrix vector products, but as I said, it can be proven that the eigenvector matrices here are all Cauchy-like. So all our eigenvector matvecs can be done using the fast multiple method, which I don't have more time to talk about, but I highly recommend you all to read more about it. Yeah, okay, there's gonna be another talk about it. Great, that's perfect. This is a very, very important algorithm, and I use it, I think, in 6 different places in this algorithm with 3 different kernel functions. So fast multiple accelerates the matrix vector products. It accelerates the root finding. You need the fast multiple to make the root finding linear complexity, and you need it to accelerate Lohner's formula. So it is essentially important. It's in a couple other places, but it's essentially important to making everything fast. Yeah, so just to, I want to talk about this. Oh yeah, also HSS operations, because of the tree structure, you can reuse a lot of the computations you have. A lot of times if you do something at one level, that's the only time you have to do it. When then you go down the tree, you already have the submatrices generated. So you're able to save a lot of log n's that way. This is how you really make it fast. So that's kind of some of the ways it's fast. Just to show you some results, I won't bore you with them, but this is compared to that bisection scheme, which at the time was the fastest thing out there to get all the eigenvalues for a symmetric matrix, HSS matrix. This is for a Toeplitz matrix. And this line is n squared. We see that ours is clearly tending towards linear complexity. And this is pretty small. Again, this only goes out to 10,000. You already see this. You get bigger and bigger matrices. The results are really clear. Where the bisection scheme, is mimicking quadratic, which is what we expect. So in terms of the accuracy is quite good, and something I'd like to mention, the accuracy is totally adjustable in these things. The things that control the accuracy, you have to set a tolerance on both the HSS construction and the fast multiple also has a tolerance. So when you use our code, you set a single tolerance. It's both those things, and that'll tell you how accurate. So for instance, these are tests where I set the tolerance to 10 to the negative 6. And we see that, well, this is small matrices. That's not, this is better, this is better. And it gives you the residual, to 6 digits for every single eigenvalue. And the orthogonality is machine precision, no matter what you set the tolerance to. So this is really good. We have accurate residual, accurate error of the eigenvalues, and residual accurate to machine precision. So about 5 minutes left. To summarize this eigensolver, well, I've told you the main points. For symmetric HSS matrices, it's linear time, it's guaranteed convergence, and we get adjustably good accuracy. The downside is it just really has to be symmetric or it doesn't work. Has to be HSS or it doesn't work. And the efficiency is tied to your HSS rank. So if you have a HSS matrix with a really large HSS rank, this starts to look more like quadratic than linear. Okay. Well, okay. So I don't have too much more time. So for the non-symmetric case, if you just want some of the eigenvalues, the way to do this is kind of doing an alteration to this feast algorithm. I don't really have time to say too much about it, but it's just using contour integration. You can think about that very pictorially and finding the eigenvalues that way. The keys here is that it is just extremely parallel. This was designed to be parallelized. It's very yeah, I don't have time for details, but I have a slide here that kind of summarizes the main points of feast that are really good. It's fast and systematic convergence. I don't know how explicit these proofs are, but it seems in everything I've seen online, the most convergent points, the most points you need are stencil points you need in the contour is 16, which is just crazy to me. And it captures all the multiplicities, it resolves that, which is something you don't get for all eigensolvers. It's very parallelizable, and you don't have to do any of that initial orthogonalization of the matrix, which is cubic and nasty. So this is a really nice thing that's been around for a while. It's not linear time, but it's really good. And we strongly believe that we can accelerate certain operations in here for the case of a non-symmetric HSS, and then get lots of the eigenvalues that way. But this won't get you the eigenvectors or the whole set. Okay. So if you do want all the eigenvalues and eigenvectors, well, you maybe can't, but let's say, but if you want the whole spectrum, we can get you a whole SVD. And the algorithm, as you pointed out, yeah, that was a really good question, is it's really very similar. It's a divide and conquer scheme. You're really heuristically just thinking about A and A, AA transpose, 0 A transpose 0. But at every point, your updates are a lot more complicated in the SVD. So if we think about what an SVD update would look like versus an eigenvalue update, we just do some algebra. And so here, let's just say that AA transpose is just A plus this rank 1 update, where it's not symmetric. So in the symmetric case, we'd have VVT. Here it's VWT. And the key here is we can write this in terms of a symmetric update and a non-symmetric update, and then write this in terms of a matrix equation, which then we can do a surety composition on, which we're guaranteed because of this form. And we just solve the surety composition of this 2x2 matrix, which is representative of a much, much, much larger matrix. And that allows us to write the entire, it's really a rank 2 non-symmetric update in terms of a rank 1 update and a rank 1 downdate, which we have all the machinery to do. So it's a very similar algorithm to HSS divide and conquer. It takes about 3 times as much runtime for a couple of reasons. But it's still very good, and you get all the singular values and all the singular vectors. Questions about that? Okay, so yeah, this is kind of the basics. Again, these are, I'm really glad there's going to be a talk on fast multiple method, because that just permeates a lot of numerical linear algebra. I know I didn't have time to get into any of the details of anything, so I really encourage you all, please come talk to me. I love talking about HSS eigenvalue problems. And then these are some of the key references in terms of HSS eigenvalue problems. Some good papers by Jha, by Gu, by Eisenstadt. And then the more fundamental stuff is a really, really good paper by Bunch, Nielsen, and Sorensen. So, all right. Thank you all so much for listening these past 3 weeks. Appreciate it.